The topic of my final project is the ecological niche modeling of anthrax by using statistical learning methods. First of all, I would like to introduce some basic background of anthrax and Bacillus anthracis. Anthrax is a zoonotic disease primarily afflicting wildlife and livestock and secondarily affecting humans. The Bacillus anthracis is a spore-forming bacteria that is endemic to specific soil environments, which are the soils in the grassland damp with high calcium and over 60.1 pH. The Bacillus anthracis was introduced to the United States since the European colonization through the cattle trading and meat production. Nowadays, the anthrax is still endemic in some part of the United States, like the recent outbreak in Montana in 2008. However, the spatial distribution of anthrax is still poorly understood. The ecological niche modeling has been widely used for model the species distribution and also for the distribution of the disease. And there are a lot of methods that can be used for the species distribution models. For example, the profile techniques include the bioclim domain and the ecological niche factor analysis. And there are also some regression-based techniques such as a generalized linear model and generalized addictive model. And nowadays, the machine learning algorithm is also very popular in the species distribution models, such as the boosted regression tree or the random forest and also the SVM. The objective of my study is to identify the ecological niche of the Bacillus anthracis for disease control and management in the United States. So the data I have is the 160 anthrax outbreaks across the United States, and considering the length of the absence data, I'm using I generate 1,000 pseudo absence data within the study area, but outside of the 2 decimal degree buffer of the presence data. And for the environmental covariates, these covariates were extracted from the remotely sensed data. For example, I have full bioclim data that describes the temperature, precipitation, and the altitude of the landscape. And I also have 2 soil grids, which are the calcium and the pH, and also I have the NDVI measurements. The proportions used for the random draw of presence and pseudo-absence were 1:1, 1:3, and 1:6, which means that the 160, 480, and 960 pseudo-absence and the 160 presence data were consisted of 3 combinations of the subset of the data set. And these combinations were split into the 80% of the training sets and 20% of the testing sets. So let's look at the method. First of all, I'm using the generalized linear model, and initially I used the backward stepwise GLM, and I want to see what's the best set of the environmental covariates to predict the anthrax. So the GLM suggests the bio 1, bio 14, altitude, and the calcium are the best sets. But finally, considering the biology of the Bacillus anthracis, I still incorporate all the 7 covariates in my GLM model, and here is the formula. And secondly, I'm using the generalized addictive model. And as we know that the GAM is under the assumption that the functions are addictive and also the predictors are smooth. And in this study, I'm using the GAMR package to build the generalized linear model. And here is the equation. And certainly, I use the boosted regression tree to simulate the distribution. In the BRT model, the trees are grown sequentially by using the information obtained from the previous grown trees. And here is the equation, and we found that and in this study the BRT model is created in the GBMR package by using the GBM function with the shrinkage parameter as 0.001, and the optimal total number of the trees are generated by using the GBM perf function. And finally, I use the random forest. And in the random forest algorithm, it is very important to identify the number of predictors that are chosen as the split candidates. And in this study, since I'm using 7 covariates, I use m equals to 3, and the random forest model is built by the random forest R package. And the main prediction map for each model was created by averaging the prediction map of 3 data subsets. And also, I also mapped the uncertainty for each model, and the uncertainty maps for each model shows the model uncertainty over the study area, which are defined as the differences between the upper and lower boundary of the standard deviation. And as we know that for the species distribution model, the AUC is the most common criteria to assess the model performance. And in my code, I also use the MSE, but here I didn't include the MSE results in the slides. And now let's look at the results. Here we can see the first table shows the AIC of the GLM and GAM, and we can see that both the GLM and GAM, the AIC decrease when the number of pseudo-absence increase. And the second table shows the summary of the AUC, and we can see that both the GLM and GAM, we found that the AUC increase when the number of pseudo absence increase. But for BRT and random forest, we found that the AUC decrease when the number of pseudo absence increase. And according to the mean AUC, we found that the GAM and the random forest have a relatively higher AUC. And this figure shows the variable importance for the BRT model and random forest model. And here we can see that the random forest uses mean decrease accuracy to evaluates the variable importance, while the BRT uses the relative influences. And we found that 2 of these graphs suggest a very similar trend of the variable importance. The exception is the NDVI and Bio1. Now let's look at the mean prediction maps and uncertainty maps. And here we can see that comparing with the other results, the GLM is overestimated in this area and also somewhere in Montana here. So here from the uncertainty maps, we can find there's a high uncertainty in this region, and next we can find the mean prediction of GAM shows the overestimated in the Texas region. It looks like that the whole South Texas is regarded as the risk room for anthrax. But however, when we look at some of the previous literature, we found that only the western coast of the Texas is regarded as the risk room for anthrax. But the uncertainty map for GAM is it didn't show many of the variation in the uncertainty maps here. And when we look at the BRT and random forest prediction, we found that these two distribution maps are very similar, and also the uncertainty maps are very similar. So, for the discussion and conclusion, we found that from the AUC, the overall prediction of the random forest and GAM was slightly better, and some of them even had some perfect models. And however, when we looked at the distribution maps, we can find that the random forest predicts better than the GAM. Um, my results also proved the Barbet-Mason's suggestion of the selection of pseudo-absence. He suggests that for the linear models, we probably need a large number of the pseudo-absence, and for the machine learning algorithm, it will predict better if the number of the pseudo-absence is relatively small. And in his study, he suggests the equal weights of the pseudo-absence and presence data for the machine learning algorithms. So, for the future work, I think I'm going to do more random draws. For example, I'll probably do like 20 random draws for each ratio. Like I probably will do like 20 random draws for 1 to 1, 1 to 3, and 1 to 6 respectively, and average them to reduce the model sensitivity. And also, I think I will compare the machine learning algorithm with the genetic algorithm model, and see what's the difference between these two kinds of the methods. And that's all for my presentation. Thanks.